A very good evening, dear students. Myself, Dr. Rajeshri Dua. Today, I am going to present Unit 3, that is the topic of wind energy of the subject Renewable and Non-Conventional Energy with the subject code PEEE 501C. We have already discussed about the Unit 1, Introduction to Energy Sources, and Unit 2, that is Solar Energy. Next comes Unit 3, that is Wind Energy. So the course objectives are as follows. We need to have an understanding about the principle of wind energy conversion, the basic components of it, the different components of the windmills, the design consideration for it, the analysis of the aerodynamic forces, and a little bit idea about the site selection consideration and wind data estimation. So coming to what is wind energy. Now, wind energy is an indirect form of solar energy. Why? Because the sun heats the earth's surface, and because of the uneven heating of the earth's surface, what we get is that the winds. So, wind results from air in motion, and there are two types of winds known as local and global. So the conversion of the kinetic energy, that is the energy in motion of the wind, into mechanical energy that can be utilized to perform work or to generate electricity via some wind generators or Reno generators. It's basically known as the concept of wind turbine. And the sails, the vanes, the blades, that we used to do in the previous times when we used to sail boats, then this concept of the air in motion, converting it into useful energy was used. So, if the axis of the rotation is horizontal, it is known as horizontal axis, and if the axis of rotation is vertical, it is known as the vertical axis, wind turbines or windmills. Now, coming to the concept of that electric generator, it is also known as a aerogenerator. And one can say that although windmills have been used for more than a dozen centuries for grinding grain, pumping water, however, the large scale electricity power generation is used there that has been developed over the past 50 years. And the first or the largest wind generator was built in recent times. That was the 800 kW unit operated in France. Okay. Now, coming to the power in the wind, it's very, very important how much the wind has the power and how much the power or the energy that we can extract from the wind. So, wind possesses energy because of the virtue in motion, which is known as the kinetic energy. So, any device that is capable of slowing down this mass of moving air, like a sail or a propeller, it can extract a part of the energy and convert it into useful work. So there are three factors that determine the output from the wind energy converter. One is the wind speed, one is the cross section area of the wind swept by the rotor, and another is the conversion efficiency of the rotor, transmission system, and the generator. No device, however well designed, can extract all of wind's energy because the wind will have brought to a halt if the entire energy was extracted and prevent the passage of more air. Okay. So, uh, what we can see is that the most possible option is that to rotor to decelerate the whole horizontal column of intercepted air to about one third of its free velocity. So, a 100% efficient aerogenerator would therefore only be able to convert up to a maximum of around 60% of the available wind energy. Well designed blades can typically extract about 70% of the wind energy. So let us now have an expression or a mathematical expression of the amount of power in the wind. So the power in the wind can be computed by using the concept of kinetics, and it's very, very important for the exam purpose of students that you need to have an idea how we can generate the mathematical expression. So the windmill basically works on the principle of conversion of kinetic energy into corresponding mechanical energy, and we know that the power is equal to the energy per unit time. So the energy available is the kinetic energy. So what we will do, the kinetic energy of any particle is equal to 1 half its mass times the square of the velocity. That's half mv square. And the amount of air passing in unit time through a area capital A with a velocity v is a into v. And therefore its mass is equal to the volume multiplied by density. So we can say that m is equal to the air density into the cross sectional area into the velocity. So m is rho av. If we put it here in the concept of half mv square, so it becomes half rho av cube. That is a power in watts. So this particular equation, it tells us that the maximum wind available, the actual amount will be somewhat less because all the available energy is not extractable. So what we can say from this expression is that this power is directly proportional to the density of air, that is 1.225 kg per meter cube at sea level. It may vary 10 to 15% during the year because of pressure and temperature change, but it changes negligibly with water content. And the equation also tells that the power is proportional to the cross sectional area of the wind turbine, that is intercept. All thus, aeroturbine C with a large area has higher power than a small area machine, but there are added implications. Since the area is normally circular of diameter d in horizontal axis air turbines, we can write A as pi by 4 d square, the square meter. So if we put it in this equation, we get P is equal to half rho pi by 4 d square v cube, or 1 by 8 rho pi d square v cube. Okay, d square v cube. So this is the available wind power. So it is dependent upon the diameter also, diameter square, velocity is cube, and the air density. So, what we can have is a graphical representation of this variation. So, in the x-axis, we have the wind speed. It can be meter per second or it can be more. So, we have taken meter per second. And in the y-axis, that is the total wind power in megawatts. So, we are also having another y-axis of the rotor diameter. So, rotor diameter 60, rotor diameter 40, rotor diameter 20. So, diameter squarish are they directly proportional. So, as the diameter increases, the wind speed also increases. So the equation tells that the maximum power available from the wind varies according to the square of the diameter of the intercept area, or the square of the rotor diameter, normally taken to be the swept area. Thus, doubling the diameter of the rotor will result in 4 times increase in the available wind turbine, and it is directly proportional to cube of the velocity. So velocity is also a very important factor. So this is the dependence of wind power on the wind speed and the rotor diameter. So now moving to another very important aspect, that was the power available in the wind. Now this particular topic says what is the maximum power that we can get as output from a wind turbine. So the derivation is very important as said, and what we can see that only 59.3% of the energy can be extracted from the wind turbine. So this is also a concept of the power coefficient, and its idea comes from the Betz criteria. So what we do is that we write the expression of this as this 1 by 4 a rho u0 square minus u2 square into u0 plus u2. So the power output depends on the output velocity u2. So for the maximum power output, what we'll do, we will make the derivative with respect to e2. That is dpt by t u2 is equal to 0. So this particular equation, if we do the derivative, so this is the first term, simplifying comes the second term, then the third term. Here what we do, 2u2 u0 k, 3u2 u0 minus u2 u0 by we are dividing. So from here, taking 3u2 common, you have u2 plus u0 minus u0, u2 plus u2. So u0 is the initial speed, u2 may be the output speed. So u2, it can be written as v, it can be written as u, whatever is applicable. We can write small v also. So v2 plus v0 plus 3v2 minus v0 is equal to 0. So from here, if we say that this is a negative value, it's unacceptable. So it is the initial velocity by 3. So if we put it in this expression, we will get this minus this square into this plus this. So if we do this, so this will be u2 square into 8 by 9, because this thing will be u0 by 3 and u2 plus u0 by 3. So this is this. So if we do this, this will come as this. And so 8 into 4, 9 into 3, and 4 gets cut. So 8 by 27 rho a v0 square by u0 square. So এটা থেকে যদি we will consider, so what we have got, half. So this comes as, take it as half, 16 by 27. So 16 by 27 is 59.3. So the maximum power available from the wind turbine is 59.3% of the input power of the power available in the wind. This expression is very important. This derivation is very, very, very important. So you have to derive taking into consideration all mathematical aspects. So now coming to the concept of wind turbine aerodynamics. The wind carries with it the kinetic energy. So aerodynamics is the concept of that. So what we do is that there should be a rotor. Rotor na thakle to we cannot get the wind stream. So the wind turbine extract energy from the wind streams by transforming the kinetic energy of the wind into the rotational motion of the rotor. The wind energy is extracted by the rotor of the wind turbine as it has one or two or three blades having aerofoil shape, and these blades are attached to the hub. Okay. Now, solidity. Solidity is defined as the ratio of the projected area of the rotor blades on the rotor plane to the swept area of the rotor. What is the impact of solidity? High solidity rotors use drag force for rotation, and these rotors they turn slower. Whereas low solidity rotors they have slender airfoil blades, and these rotors use lift force for rotation, and they turn faster, very faster. So this is the concept of solidity. Now coming to few terms related to wind turbine aerodynamics. So this is the figure. So this is the cross section. So this is a rotor blade and this is the aerofoil shape. This spindle shape or aerofoil shape is also seen for aeroplanes. Okay. So this is the chord is actually the width of the blade which is across the distance from one edge of the blade to the other edge. So this edge to this edge, this width is known as the chord. Now coming to the wind turbine aerodynamics and the concept of the different velocities. The first velocity is the wind velocity. The velocity of free airstream at sufficient distance away from the wind turbine where there is no disturbance due to the rotation of the wind turbine is known as the wind velocity. Okay, now coming to the concept of incident wind velocity. So it is the velocity at which the wind strikes the blade. This velocity is a little slightly lower than the velocity of the free airstream. Now coming to the concept of blade linear velocity. So this will be u1. So this is the concept of the blade linear velocity, that is v. So blade linear velocity is the tangential velocity of the blade due to the rotation, and if omega is the angular velocity of the blade and r is the length, then the blade linear velocity is v is equal to omega into r. And what is relative velocity? Vr. So this is v blade linear velocity. This is the incident velocity. This is Vr. That is the relative velocity. It's the relative velocity of the wind with respect to the moving blade. It is the vector sum of the incident wind velocity and the blade linear velocity. Mathematically, it can be given as Vr is u1 plus v. So, this is u1, this